so we're going to dig deeper into determinants a little bit more, or just at least be able to find them, and then you know, use them to help us find the eigenvalues and eigenvectors. So they start off with having us try to remember that the determinant of a 2 by 2 matrix is the product of the diagonals minus the product of the wings. And we want to see if we can extend this to a 3 by 3. Well, it doesn't quite extend like that because this has the diagonals, but this doesn't have wings. It has like 3 other elements on the other parts. And so what they do, and what they do in most cases, and even in Calc 3 when they talk about the cross product, is that they define it for you, and then they give you little tricks of how to find them a little bit quicker. But the idea behind this definition is an expansion, a walk along. I guess an expansion would be a little bit better. An expansion along a particular row or column. So if you notice, these things will actually be constants, or elements in the matrix times a determinant of a submatrix. So let's see. If I use a triangle for A1, when you cross out the A1, you would have this submatrix left over, which is a 2 by 2. So if you cross out the row and the column where A1 is, you have this 2 by 2 matrix, which now you can find a determinant of, because we can find determinants of 2 by 2 matrices. So that all kind of stems from the idea of knowing the determinant of 2 by 2 matrix. Victor?
So where do you do a determinant? What's different about this?
Say it again?
Where do you do a determinant?
Then take a little nap and wake you up. Yeah, it's the same thing. Okay. But after we establish some of these definitions, we'll get into some deeper theory of determinants that might be a little bit more meaningful. So the next step is to, if you're running along, in this case it's going to run along the first row. If you run along the first row, your next element in your row is the 1 by 2 matrix, and if you cross out the row and column where the 1 by 2 matrix is residing, what you have left is another 2 by 2 matrix that would make up your 2 by 2 matrix that you're going to find a determinant of.
Is this called Cramer's rule?
No. Cramer's rule is a way to solve for systems of linear equations that uses determinants. But determinants really play a big part in it. And we'll take a look at Cramer's rule later on. And finally, if we continue on running along here, I got a triangle, a circle, what's next? Square. Red and orange look alike. How about blue? So if we take that last element, it now, after crossing out the row and column that it belongs in, we can look at the 2 by 2 matrix that's left over, and we're going to find a determinant of that. Now, I think there's one thing I didn't address in this whole plan here, and what is it? A negative sign. So the negative sign over here does play an important part in this. And how do we determine the negative signs? So it turns out that when you walk along a matrix like this, you're going to start off with the first element as being a positive, and every time you take a step along the row or column, now you can't go diagonal here, you can just go along a row or along a column, you're going to switch your sign. I guess that should have been in green. A row or column, if you take a step to the next row or if you take a step to the next column, I said that backwards. If you take a step to the next row or next column, then you're going to have a sign change. And then the last one is going to be positive. So there's a sign contribution depending on the position that you're in your matrix. Okay? So does this make sense?
I think it worked out right.
I don't know. I don't know why it works that way. No, there's an answer that I can't remember right now. There's some meaning behind it where there's a meaningful answer to this, and I can't think of it right now. Yeah. Oh, the capital A. Our notation for determinants will be the absolute value bars. So when we have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 10. When this is our matrix and we want the determinant of this, the determinant will be denoted by a vertical bar with whatever the matrix is. So whether we have actual numbers or we're using the symbols A, B, C, or whatever, when we use the vertical bars, that means the determinant. I guess I didn't lay this out. I thought we talked about determinants on Monday. Well, if we had IJKs up on top, then it was a cross product. But so the determinant is not the cross product, but the way to find the cross product requires you to take a quote determinant. And I have to say quote because, like I said, the top row is IJK, which are vectors, is not technically scalars. So what they do in Calc 3 was that for us to compute the cross product, they invent notation to make it easy for us to be able to compute cross products using determinants. All right. Now, if we look at this technique where we run along a row or a column and expand on it, we can kind of see that in the 2 by 2 matrix. Now, this is kind of silly to do this, but I think it's worth taking a look at because from here, normally we would say, oh, let's make it for larger matrices like 4 by 4s or n by n's. But let's go backwards for a minute and take a look at how this is going to work with a 2 by 2 matrix. So let's say you had A, and this is a 2 by 2 matrix, 1, 2, 3, 4. Or let's make it A, B, C, D. And what we could do is we can run along a row. So if, for example, we want to set A and then B as how we're going to expand, then we're going to say, I'm going to have A, and then I'm going to cross out the row and column where A is in, and I'm going to find the determinant of D. Now that's kind of silly because D is just a scalar. It's not a matrix. So if we think about the determinant of D, well, this is really just D. And if we take our next element, remember that this is a minus because we moved from the first, the 1 by 1 spot to the next spot. This will be a minus, and then we'll have B times the determinant of what happens if we cross out the row and column where B is in, then I get C. And the determinant of, again, a scalar is just itself. So we have our formula for a determinant of a 2 by 2 matrix, AD minus BC. Okay? So, this whole sign business, how the sign changes, is again dependent on where you are in the matrix. I don't know if I have I don't have a picture of this, but I think the book has a picture of this. So let me add on. Sign changes. And if you have a matrix of any size, each element in the matrix is going to have an assigned sign, positive or negative, and it really just alternates from the first slot. So positive, negative, positive, negative, positive, negative, etc. And if you go down, the same thing. Positive, negative, positive, negative, positive, negative, etc. And so as you keep going, there's going to be a sign change here. Positive, negative, positive, negative, positive, negative, positive. So there's going to be these sign changes, and that's going to, those are the signs that are involved in when you're expanding along a row or column. Roman?
So it looks to me like we're only traversing over the column.
Yeah.
We're traversing over the columns, but it turns out that you can traverse over any column, any row, and yes. So we're traversing along the first row, but it turns out that you can traverse over any row or any column, whatever might be more convenient. And depending on the type of problem you have, the type of matrix you have, you might want to consider traversing over a specific row or column that would make things easier for you. And what I mean by that is that if you have a row or column that have the most zeros, that's probably where you want to go. Anyways, these signs, if we take a look at the ith, jth element, so the ith row and jth column, whatever that is, will have a sign that's -1 to the, and if you look at I plus j, that's going to be +1 or -1 depending on where you are. And so this is how you figure out the sign for the position that you're in. So in 1, 2, 3, 3 by into 3 and 4. The third row and the fourth column will have a sign that's -1 to the 3 plus 4. -1 to the 7th is equal to -1. And so we have a negative sign in that slot. So you probably won't need this formula or this formula, because when you're traversing, you just remember, or try to remember, it's positive, negative, because you're just traversing over one row or one column. But if for some reason you need to find a sign for where you are in the middle of the matrix, then you can just figure out which row and which column you're in, and that's going to be the sign that's going to be associated with that. Now, there are formulas in the book and a lot of other places where it could look a little confusing because it requires a little bit more with the definition and stuff. Oh, this is still a 3 by 3. Yeah, there's one with n by n. So the idea with this, still working with a 3 by 3 matrix, the this is still a 3 by 3, sorry, for in an attempt to generalize this to an n by n, we kind of want to generalize this for a 3 by 3, and when I say generalize, I mean try to put it in a formula of sorts. So what we're doing here is we're looking at a 3 by 3 matrix. Why don't I just copy? The idea here is that looking at a 3 by 3 matrix, we can try to generalize this by walking along a specific row, in this case the first row, where the sign will change and the element in that ijth, or in this case first row and jth column, how the j column changes. And then we're looking for the A1j. This is the subdeterminant, so to speak, when you cross out the first row and the jth column. And so A1, or capital A with a subscript ij, is called ij minor. And then in the book they define a Cij, that's the Aij with the sign, positive or negative. So that's just a way to rewrite this formula where you have one notation that includes the other piece of notation. So so now that we've established the formula for a 3 by 3, we can generalize to an n by n. And this is the formula for finding the determinant of an n by n matrix by expanding over the first row. Okay. Should have taken some snapshots of some homework assignments. It should be 4.2 already. Wait, is it? Well, they only have 3 by 3 matrices here. I was looking for larger matrices to mess around with. Where is it? Do we have any big matrices here? No, let's do number 13. So I'm going to do this the way we got it set up, where we're expanding the first row. And then after we introduce another theorem, we'll redo the same problem where we get to choose which row or column we're going to expand. But let's do it expanding on the first row. So according to the definition that we just had, we can find the determinant of this by going through the first row. So I'm going to say this is my first one. That's 1. And then I'm going to multiply after I cross out the first row and the first column, because that's the spot that it's in. I'm going to get this submatrix. So this is 5, 2, 6, 1, 0, 0, 4, 2, 1. And then for my next step, I'm going to say negative, and then I'm going to take that -1. I have to alternate, right? So this is my negative sign that alternates, and this actually is -1. And then now I need to cross out the first row and the second column, and then what do I have left? My submatrix is 2, 2, 6, 0, 0, 0, 1, 2, 1. My next step is to go running along the first row. I would have a plus and then a 0 times, I know I don't need this, but let's figure it out anyways. 2, 5, 6, 0, 1, 0, and 1, 4, 1. And then finally, remember that the sign changes to a -3 or to a negative, and then so I have that constant 3. Cross out the first row and first column, and then I have 2, 5, 2, 0, 1, 0, 1, 4, 2. Okay? Now for each of these, I would need to find the determinant of a 3 by 3 matrix. So I have 1 times the determinant of a 3 by 3 matrix. Now if I want the determinant of this 3 by 3 matrix, I'm going to need to expand again. So I'm really going to do this, huh? So I have 5 times the determinant now of a 2 by 2 matrix. I got 0, 0, 2, 1. And then I go to the next column, 2 with a negative sign. The submatrix is 1, 0, 4, 1. And then I go to the next one with a positive, that's 6. And then I get 1, 0, 4, 2. Do you get the picture? All right, I don't want to continue on anymore because we're going to find it a different way. Did you?
So for the green one, if you chose the second row, would that automatically make everything 0?
Yes, but that's going to be the theorem that we're going to come up with next. Do you see what she said? If we choose to expand on the second row, that whole thing would be 0. And that would make our computations a lot easier. In fact, if we look at the original matrix, there's going to be a specific row or column or something that we can expand on that's going to make our computation a lot easier than what it is. All right? So I'll put ... here, and we'll do it a different way. But before we do it a different way, we have to know why we're going to be able to do it a different way. And so the next theorem, called the Laplace expansion theorem, not to be mistaken with Laplace transformation, for those people in my differential equations class, or if you're taking differential equations. The Laplace expansion theorem allows us to expand on any row or any column. So let us put that expansion theorem in our notes and not prove it and use it. Use it using the matrix that we were just looking at earlier. So if we take a look at our previous example, and the Laplace expansion theorem tells us that we can basically expand on any row or any column. I think this should be an I and J. Yeah, I need to fix that in my notes.
Whoa. The other ones as well.
On the other ones, I was assuming I'm expanding the first row, and so it should have been a 1. But I copied and pasted, and I forgot to change these things. Or I changed it incorrectly. Anyways, if you had a choice on which row or column to expand on, which one would you choose? If you look at the third row, you got some nice zeros going on there. All right? And so because they're zeros, we know that they're going to have a 0 contribution. So let's get the sign correct here. This is a positive, this is a negative, this is a positive. So if I were to expand on the third row, I would start off with a positive here, a negative for 1, a positive for this 0, and then a negative again for this 0. Not that we're going to use that, but because it's 0. But if we expand on the third row, these are the signs that we're going to be looking for. You can't get this. There you go. Disappear. So this is going to expand as, I don't need to put this, 0 times the determinant of something. Now I have a -1, so this is what's going to count. I'm going to cross out the row and column that that element is in, and I'm going to have my submatrix, the 1, 2, 3, 2. So the 3, 2 minor, they call it. That would be a 1, 2, I should be reading it across, huh? 1, 0, 3, 2, 2, 6, and 1, 2, 1. So expanding along the third row, you'll have a bunch of 0 contributions that you don't need to even worry about. And so now you're just focused on this. Now I want to expand. I need to expand on something else because this is not a 2 by 2 matrix. I don't have that off the top of my head easily. So what are we going to expand on? So probably the top row, because that one has a 0 sitting there. So this is going to be a 1 times, and then the submatrix with a 1 would be a 2, 6, 2, 1 minus a 0, and then plus 3, and then the submatrix there is 2, 2, 1, 2. Okay, so we got another 0 to disappear. And now we have 2 by 2 matrices, which is easy to handle. So we got a -1 on the outside. We have a 2 minus 12. I'll put 2 minus 12. Plus 3 times 4 minus 2. So -1. -10 plus 6 negative, negative 4, positive 4. So the determinant is positive 4 with minimal amount of work compared to, boy, whatever it is we were doing over here. Instead of trying to expand now, you know, these three matrices, the theorem allows us to select a nice row, and preferably, or column, preferably one with zeros and stuff, so that we can wipe out a bunch of things. Question? Did I do it right? Feel like I should put it in Mathematica just to check, make sure I got it right. It's right? Okay, good. All right. So, determinant is some special operation with a matrix that takes a matrix and gives you a scalar, a value, a number. And so there are special properties that we probably should consider, especially when we start combining matrices, like adding matrices. Or if we have special types of matrices, then maybe determinants should be a quick way of finding determinants. All right, let's take a look at the determinant of a special type of matrix. Triangular matrix. Do you remember what a upper triangular was? Like the bottom is 0, and when you say bottom, you mean bottom left, right? Right or left. So let's see. When we have an upper triangular matrix, and this is kind of a pseudo proof to this, A11, A22, A33, and then I'll put stars here and zeros down here. Say it's an upper triangular matrix. We can imagine expanding along the first column. That would be the easiest probably, right? Because here you have a bunch of zeros. So if we expand along the first column by Laplace's theorem, we can get the determinant that way. When we do that, we're going to say A11 times the determinant of a submatrix that we get when we cross this stuff out. So this would be A22, A33, A44, dot, 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 zeros here, and some other stuff that may or may not be zero in the upper part, plus a bunch of zeros, because we would have expanded there. So, okay, so that's our first step. Next step is that we have to take the determinant of this submatrix. Well, if we take the determinant of this submatrix, I would probably want to expand on the column again, right? A bunch of zeros here. I want to expand on the column again, and then I want to get this submatrix. So I have my A11, and now my A22 times A33, A44, dot, 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 stars and zeros. So that's my next step, and then if I go one more step over here and decide that I want to expand on the column again, where I know that there's going to be zeros, then I get A33. So you see that there's a pattern here that, again, not a formal proof, but it seems pretty obvious from here that the sum, or not the sum, but the product of the diagonals will end up being your determinant. So all you have to do to find the determinant of an upper triangular or a lower triangular matrix at that is that just take the product of the diagonals, and everything else can be ignored because you would have expanded along the first row or first column to get the result. Okay? So if we have this kind of a special matrix, we got a quick way of finding the determinant. Easy. What? What?
Wow, really? You can ask that?
Oh, I don't know. So properties of determinants. A bunch of properties here that look like they're important. And let me see if I can, well, I'll just leave it at that. These are some important properties for determinants that might be useful for computing determinants and anything else that might be related to determinants like eigenvalues and stuff. So without formally proving any of these, we can kind of take a look at a few of them and see how they would kind of work out. Number A here, if A is a 0 row or column, then the determinant is 0. So it turns out that for this particular property, if we imagine it doesn't have to be the first row, it could be any row or column. If you have zeros in any row or any column and you decide, well, why don't I just expand on this column, then everything is going to be multiplied by 0 and then you're done. So the determinant of this is equal to 0. Okay? Yeah?
So it doesn't matter which way we choose to evaluate the determinant, we'll get the same one.
Yes, correct. And that's why I kind of wanted to do this, but I didn't do it. To show you that we would have gotten 4 here and say, okay, that took a little bit of work, but if you were to do it choosing any row or any column, then you would get the same result. And that is due to this Laplace expansion theorem. Yeah?
So, is that why when you're trying to find lambda, you want us to the determinant equal to 0?
No, that wasn't the reason why. The reason why was because the null space of that thing, we want that null space to be not 0. And so if the determinant was equal to 0, then the null space would be 0, and then you would have none. So that's why. So it's a little bit different. If you exchange a row or a column, it turns out that the determinant of B will be negative of the determinant of the original matrix. Why is that?
Does it depend on when we do it?
Say it again?
So can we do more than one row interchanging? And I'll split these into pretty specific.
Well, let's put it this way. If you do one interchange, then it'll be negative. If you do 2 interchanges, then it'll be positive.
All right.
Yes. So why is this true? Let's see if we can justify this with some pictures and drawings and stuff. Let's say you got A, B, C, and X, Y, Z, ... as some row and some column that you have, And when you expand it on x, y, z, or a, b, c, let's say you expand it on a, b, c, you're going to have a minus b plus c. Oh, no, I don't think this is going to work.
It's not going to work.
It's not going to work.
Because, yeah. Anyway, you see why it doesn't work.
Yeah, because it's all kind of arbitrarily.
Switch two rows that were two apart.
Never mind. You know what, this would be better proven if we talk about elementary matrices and some other stuff with elementary matrices. So we'll prove this later. For now, let's just erase it. I could, but I want to have the motion of erasing it. So for those people that are taking notes, I feel your pain. Okay.
The writing pencil.
Yeah, when you interchange row and columns, you'll see, and we'll introduce this idea of the elementary matrices and then determinants of products, and this will come a little bit better. If two rows are identical, then the determinant's equal to A, or determinant of A is equal to 0. Is there a quick way of doing that?
And it just uses the. So if you interchange them and negates it, but it has to be the same as the other one. Because you didn't really
Yeah.
make it, so it has to be 0.
Provided that we know B. So assuming that B is correct, or B is true, this would be a good proof. This is a proof technique. If you have two identical rows, A, B, C, A, B, C. So let's say this is A. Then the determinant of A is whatever it's going to be. Let's give it a value. Determinant of A equals X or something. Now, if we interchange the two of the rows in A, if we have two of the same rows, two rows that are exactly the same, and we interchange them, what's going to happen to the matrix? Nothing, right? If I interchange A, B, C, and A, B, C in these two matrices, then it's going to be exactly the same matrix, right? Now, according to this interchange, I guess this should be B now because it was interchanged. So it's a different matrix, but it's really the same. So if we interchange two identical rows, then it's going to be the same matrix. So the determinant of A is, according to property B, and when I say B, I mean this B. The determinant of B is equal to negative the determinant of A. But we also note that B is equal to A, so determinant of B should equal to the determinant of A. So it's like X, negative X is equal to positive X. Yeah. Well, it's the only way this will be true is that if X is equal to 0. So if you solve for this, right? You solve for this, right? 2x is equal to 0, x is equal to 0. So you get to conclude that the determinant of A has to have been equal to 0 for this to be true. Okay. All right, let's just read through the rest and not try to justify it. If you multiply a row or a column by k, then the determinant of B is going to be equal to k times the determinant. I guess that's easy enough to do. If we think about the expansion, you're adding up a whole bunch of things along. If you expand along that row, imagine factoring out a k. And then, so that's a k factored out, and then you have just a regular determinant. A, B, C are identical except for the ith row or column of C is the sum of the ith row. Then it's adding the rows and whatever. F is similar to a row operation, which is what we're going to do next. But if we take a look at this, if B is obtained by adding a multiple of one row of A and adding it to another row of A, then the determinant is the same.
We have like some extra word. I'm getting confused. It's like he
Where?
He uses it 3 times. Adding multiple one row column A, another row column A, another row.
Dang, copying and pasting. I don't think this is a copy and paste problem. I think I was just typing this up and must have been watching TV or something. Is that better now? Adding a multiple of one row of A to another row, then, okay, that's better. Do you ever do that when you're copying stuff and then you look away and then you copy, try to look at where you left off and then something like that on your test. All right, let's get past this and move on. So something a little easier and lighter is taking a look at the determinant of elementary matrices. By the way, the determinant of an identity matrix is 1. Right? So determinant of identity matrix, doesn't matter what size it is 1 because it's just 1's in the diagonal, 0's everywhere else, and according to the upper or lower triangular business that we saw, it's just the product of the diagonals, and if we're talking about the identity matrix, they're all 1's. So E is an elementary matrix where you interchange 2 rows, then the determinant is equal to -1. So we didn't, that's when we were trying to prove earlier, and I couldn't do it, so let's see if we can prove it with an identity or an elementary matrix. So for this, let's just do a quick example and see what's happening, what's going on. So let's say this is your elementary matrix and we switch to first and second rows. Let's do a 3 by 3 just to make things easy. So this is the result if I switch to first and second rows of the matrix. And let's do an expansion to find the determinant of the matrix. So the expansion is going to, let's expand either row or column. So if we expand along the first row, we're going to get a 0 times some matrix with a plus. And then the next one is going to be a -1 times the 2 by 2 matrix, and we're going to get left as identity. And then plus 0 times another matrix. And so we get -1 times 1. So it looks like it is the negative of the determinant of the regular identity matrix, so that must be true. That's not how we prove it, but we would, if you really want a proof of this, we would get the definition or get the Laplace expansion definition and then prove it that way. All right, so this is, let's not call it a proof, let's call it a little example, illustration, and let's leave it at that. For B, if we if we let E be the elementary matrix where we multiply one of the rows by K, and let's see what happens there. So let's multiply the second row by K. Then in this case, the determinant of E, we can expand by anything. Well, let's expand by the first row. So I'll start off with the 1 here with a positive sign. So 1 times the determinant of the, actually I don't have to do that. This is a diagonal, right? So 1 times K times 1, which is equal to K. Okay. And the last one I think is most interesting because you're introducing, you're adding a multiple of one row, so you're introducing another factor, or another factor in there that you're adding onto another row, and yet it's still not going to make a difference. So let's take a look at how that plays out in a 3 by 3 matrix. So let's take the first row, let's multiply the first row by 3, add it to the second row. And then we have this matrix, right? Now, the determinant of this matrix can be found by expanding over any row we want, so, or column. Any suggestions on which row or column? I probably don't want to do the first column because there's 2 non-zeros there. So if I choose a first row or second column or whatever, third row, let's do the third row. So if I start from the corner here, I have a plus, a minus, a plus, a minus, a plus. So my 3 by 3, the third row and third column element will have a sign that's positive. And if I'm going to expand over the third column, I need to know that, right? I need to know the signs for each of these terms. So I'm just going to expand on this. I know that I'm going to have a bunch of zeros, or a couple of zeros, with a positive and a negative. And then I have a positive with a 1 in there. And my submatrix is going to be a 1, 0, 3, 1. And then if I find the determinant of this, this is just 1, right? 1 minus 3 times 0, which is 0. So our determinant is going to end up being equal to 1. So it didn't really matter what we multiplied the first row and added to the first column by, or a second row. First row added to any row, or even the columns. If we take the second column added to the third row, this expansion will somehow, when you break it down to the 2 by 2 determinant, wherever that factor that you multiplied the row by will end up being multiplied by 0, so it'll disappear. So it doesn't really matter. Okay, so far? So we're done with the elementary matrices, and the only thing to remember is that if you multiply one row by something, okay, if you switch 2 rows, then you get a negative for the determinant, and then that last one is just going to be determinant of 1. So we need one more theorem, and that's a theorem, or I don't know if they call it a theorem or a property, but once we know that, we can backtrack to the other theorem that I couldn't prove real quick. Lemma. Lema. A lemma is like a prelude to a theorem. Prelude. A lemma is like a mini theorem that's used to prove a bigger theorem. That's what they call lemma. So there's a lemma, you set up a bunch of lemmas and you prove a big theorem, and then anything that follows after a big theorem is called a corollary.
Wow. We got these names. It's cool though, too.
So this talks about if you have an elementary matrix times another matrix, then you're going to the determinant of that product is the product of the two determinants. So this is, I know this is probably not fair because technically when you do a lemma theorem corollary, you have to do it in that order. And here we have a theorem and a lemma, and never mind, it's just some weird stuff. Anyways, back to that thing where you say that if you interchange two rows, you get the negative of the determinant. Remember that? Where is it? The B that I attempted to prove and failed miserably. So I want to take this statement and say that that statement really just follows directly from this. So if we have A is a matrix, right? And then any n by n matrix. And then we'll let E be an elementary matrix with a row switch. With, I should just say with. With one row switch. Then E applied to A is going to be a new matrix where you interchange two rows of A. So interchange okay? So if that's true, then the determinant of B is equal to the determinant of the product of E times A, which according to this lemma is equal to the determinant of E times the determinant of A. Right? So the determinant of an elementary matrix with one row switch is -1. Because if you switch one row, because of this theorem.
Yeah.
We didn't justify it, we just gave an example.
We can fix that.
Well,
We never fix
if you change it one time, then your determinant is going to produce a negative sign. So that's what we did over here. We switched it by multiplying your matrix with an elementary row operation. It's like actually doing that row operation on that matrix. So this is equal to -1 times the determinant of A, which is negative of the determinant of A. So if you do one switch, that'll happen. If you do two switches, then you're really doing a -1 times a -1, which gets back to a +1. All right, and so the book goes through a more rigorous proof of this than what I'm doing. So you should read the book. Okay, so this lemma leads to a more important theorem for determinants, and that is that oh, there's 3 theorems. 4 theorems. Yeah, let's list them all down. I was looking at theorem 4.8, and I've been waiting for that. I think that's one of the more important ones, but all these other ones kind of follow. So this first theorem over here is going to relay back. Remember that we had that long list of the fundamental theorem of invertible matrices, and we had a long list of properties and stuff that were supposed to be proven. Well, here's another one to add to the list. If we have an invertible matrix, then the determinant is not going to be 0. And you notice this if and only if over here, and that implies, actually if and only if, we can change the statement around to say that if the determinant of A is equal to 0, then, and this should be an if and only if, A is not invertible. And if A is not invertible, then there's also a bunch of things that follow, like the null space business. The null space has rank, or the null space has dimension bigger than 1, or bigger than or equal to 1. So this is an important statement. If you take your matrix and you multiply it by k, when you multiply a matrix by k, it like gets multiplied on all the elements of k, all the elements of A, right? So k times a matrix, and I'm just going to do it with identity just to make it easy for us. So if you multiply a scalar times a matrix, you put that scalar and multiply every element in the matrix. So if you multiply every element in the matrix, then if you try to take the determinant of that, it's like multiplying the first row by k, the second row by k, the third row by k, etc. Well, you remember the determinant, the elementary matrix where we multiply one row by a constant is going to be k times the determinant of that matrix. If you multiply all the rows, then there's going to be as many k's as rows as you have. As many k's rows. As many rows of k, or k. As many k's as you have rows or column. Yes, that's what I meant to say. So the determinant of this is going to be k times k times k, right? So it's k cubed, and that happens to be the number of rows we have in that matrix. So if you multiply a matrix by k, the determinant of that is not just k times the determinant of A. The determinant of that is k to however many rows you have times the determinant of k, or determinant of A in k. All right. The next one I think is the most important one. The determinant of a product of two matrices is the product of the determinants. So let's just say that's that. Cauchy-Riemann? Oh. Yeah, I don't know. Yeah.
Is there like some character above the A at the very end there, determinant of A?
No, that's period. No, it's period. So the last one, if it's invertible, then you have A inverse. And it turns out the determinant of A inverse is the reciprocal. So this looks kind of, you know, fishy with the determinants and stuff like that. It's you can rewrite it like this. I don't suggest this, but determinant of A inverse is equal to determinant of A inverse, like a reciprocal. But that's just the notation. So if we know some information about the matrix, then we can find, we have a bunch of different ways now to see if we can get a shortcut to find the determinant instead of having to do that expansion. So by knowing some information about the matrix, if it's a triangular matrix, for example, or if you know that the determinant of a previous matrix that this came from after an elementary row operation, then we can find the determinants a little bit quicker instead of always using the definition or the formula. So there's this transpose. Oh, there's one more that would probably should go on that page. The determinant of a transpose is equal to the determinant of the original matrix. And that kind of makes sense because if you switch the row and columns, you can expand by whatever you expanded by in the first matrix. So if you expanded by the first row in matrix A, and then you take the transpose, the first row becomes the first column, and you can expand by that and still get the same result. So that one's kind of obvious. Yeah, obvious. It should be clear to the reader. So Fermat was proving this big theory on something, and then he put on the side of his margin on his work, a to the n plus b to the n is equal to c to the n has no integer solutions for a, b, c for n bigger than or equal to 3 or bigger than 2. So if it's 2, it's like the Pythagorean theorem and stuff like that. And then we know we have integer solution like 3, 4, 5 triangles and things like that. But if n was bigger than 2, there's no integer solutions. You can't find any numbers where n is equal to 3, for example. So he put that on the side and says it's obvious that this is true, and he didn't prove it. Well, it turns out that people that had read that manuscript tried to prove it over the years, and it wasn't until 200 years later that somebody actually proved this as a true statement. Pardon me?
In the 90s, I think.
In the late 80s. Yeah, so some guy from Michigan who worked with somebody from Berkeley and stuff like that. And this is when mathematicians do things like this, they share it with everybody because they need feedback, need to make sure it's correct. It turned out to be like a 200-page manuscript that proved this particular theory. And this is called Fermat's last theorem. If you want to Google it, you'll see it and you'll see who it was. I remember I was going through school, and then my dad gave me a Time magazine of this guy that actually proved it. I said, "Oh, cool." And I looked through it, and I didn't understand anything. All right, Cramer's rule is in your book. I'm not going to put it up, but we'll talk a little bit about Cramer's rule next time. We have one class next week on Monday. Wednesday is an off day for you guys. And for me too, but it's an off day for you guys. So we'll have one class. We'll finish up most of this chapter, I think, next time, and then I'll have more information about making up the test and what's going to be in the future for us, so that you can think ahead over Thanksgiving break. All right, see you guys.